Hello, and welcome to the first episode of CS888, which is an advanced topics in computer graphics, specifically stereoscopic 3D. So I'm Leslie Eisted, and I suppose it's time to actually discuss what is this wonderful course that we're putting forth for this spring term. So just to talk a little bit at first, obviously this course is being offered as an online only version for your health and for your safety and for everyone around you's health and safety as well. And unfortunately, that means we've had to make some pretty big changes to this course and to every course that's being offered this term. For one, as many of you probably know, seminar courses are usually courses where students read some papers and you present some papers, and then we have a rather lively discussion of said papers in person. We cannot do this. We've also been instructed that we are not permitted to have synchronous course creation or course expectations. So everything has to be offered asynchronously. So we, as I said, have had to make quite a few changes to how this course will run that I think it's going to work out, but unfortunately some of the aspects of this course that I had hoped to deliver we simply can't do anymore. Amongst that, because this is a course in Stereo 3D, it would have been really nice for you to actually get your hands on some Stereo 3D equipment. We are unfortunately not going to be able to do that anymore. We have a number of wonderful screens to play with. We have a 55-inch active shutter stereo TV, your standard 3D home TV. And of course we have a Blu-ray player and a bunch of 3D Blu-rays that we could have watched and critiqued. We also have a really cool screen, which is a 65-inch glasses-free 3D display, which is pretty awesome. And unfortunately, we're not going to get to play with that one either. And no, I couldn't bring it home with me. It is way too big, and it weighs about 200 pounds. So it had to stay locked up at the school. And there were numerous other things that we were supposed to get to do, and unfortunately, we're not going to get to do either. But the way I figure it, once this is all over and everyone's back on campus, what might be fun to do is schedule some kind of like movie afternoon, and we'll give you all an opportunity to come in and actually see some 3D technologies that we actually have access to. And at that point, hopefully you'll all have a much deeper understanding of how 3D works and what the pros and cons are, what some of the difficulties are in creating 3D content. And so you'll be able to actually very critically view some of these old 3D movies that we have. Now, who am I? Because some of you may not have seen me around. So I'm actually a lecturer here at Waterloo, and I have been here for almost 20 years. I've done all my degrees at Waterloo in CS, and now I work here, which means they consider me a lifer. My primary area of research is obviously Stereo 3D and film. And generally speaking, what my goals are is trying to find problems with film production pipelines and trying to find automated or semi-automatic ways that we can improve the efficiency of the pipeline and improve the quality of the pipeline. Because right now, and we'll talk a little tiny bit about this today, if you look at how movies are made, it's a very manual process. It involves hundreds of artists in a room manually tracing every single strand of hair. And I wish I was joking. I'm not. So, and what's interesting is a lot of the things that they do, there's no reason for them to do it by hand. Things like manually coloring irises, or doing things like detecting dead pixels from a CMOS or a CCD. It's all done by hand right now. So that's my kind of research interest, and I put a special focus on Stereo 3D because it's an area where, even though it's a very old idea, it's an idea that we still don't do very well, because from a technical perspective, there are lots of things that haven't been solved yet, or at least haven't been solved sufficiently well enough that we could actually move forward with producing much better 3D content. All right, so what I'd like to do then, our organization for today, is I would like to tell you a little bit about the administrative details of the course, what we're expecting of you, and what you can expect of me, the grading scheme, and things like that. And then I'd like to dive right into kind of an introduction to Stereo 3D, what it is, how long it's been around for, what are some of the problems associated with it, how do you capture some 3D content, and how do you view some 3D content. All right. So we're going to switch over to the split view here. And I apologize in advance if there's an echo. I think I fixed it for my other course, but I'm not sure I've got it fixed for this one. So, there we go. All right. So we have a course website. It doesn't have the traditional URL. The URL is right here. This is just my personal homepage, which I've got up and running finally. And it gives an overview of all the details, but for the most part, everything you need for this course is actually accessible through Piazza. And you should have received an invitation to our Piazza group. And if you have not, please send me an email right away and we'll make sure that you get logged into Piazza as soon as possible. From the grading perspective, so 50%, there's no exams in this course. It's an 800 level. There shouldn't be an exam. Nobody likes exams. But there is a final project. It's worth 50% of your final mark. And we'll talk more about your project another time. Well, in a few minutes. And then 20% of your final grade is for paper presentations. So I'd like you to choose 2 papers from different areas and present them. And how I'd like you to do this is by actually recording yourself presenting that paper and uploading it. And we'll discuss more on Piazza exactly how to make that work. Then I would like you to do, and it looks like I have neglected to update this. It says 4, it should be 8 paper reviews. So 8 paper reviews, not 4, worth 2.5% each. And I'd like you to choose 2 from each area. I'll make sure I update these slides, and then I'll post them, of course, to Piazza as well. And then I'd also like you to do some participation. Now, normally participation would be in-class participation. Do you actually discuss things? Do you ask questions? Do you answer questions? And since we're not doing any kind of synchronous course deployment, or we're not going to see each other in person, this is going to be marked as, are you actually asking questions of other presenters on Piazza? Are you answering the questions that people ask you? And we're also going to ask you to view and offer feedback to 24 of the paper presentations. Now that probably seems like a lot of work, but the paper presentations should only be about 10 or 15 minutes. So 24, that's about 240 minutes. So if you were to have 2 lectures a week, that would be 240 minutes. So it's actually not that much work. Now, for those of you who may not be so comfortable with Stereo 3D, or maybe those of you who are a little bit wary of a 50% final project, there is an optional assignment, which the details aren't quite all posted to Piazza yet. I'll get them posted shortly. The optional assignment is worth 10%, and it would reduce your final project grade to 40% instead of 50%. And what the optional assignment is going to be is, I have 2 papers, and you would simply choose one of those 2 papers to implement yourself. Now, if you're thinking this probably sounds really complicated, they are actually quite simple papers. But they're kind of fun, and they have some pretty cool results. And it would give you some good coding experience with 3D, and just some good hands-on, how does this actually work? So your final project, and I have a whole document about what constitutes a final project, what is the breakdown of the final project grades. Of course, there will be a proposal, and then you have to actually have some deliverables, things like a presentation. You'll need to have also a paper writing about what you've done, and then any results. But to give you some incentive to do some more creative projects, so first off, you can do different kinds of projects. You can do something like just a paper survey. It's not worth as much as, say, doing new work, but a paper survey is one possible kind of project. Repeating somebody else's experiment is another possible project. But if you do something new, if you try to attack a problem in 3D, and there are so many problems to choose from, and I will help you out with this because I'm actually going to give you an ever-growing list of some things which I think are bite-sized. If you do some new work and your results are publishable, that is within reasonable expectation, if we submit it to a conference, it would probably get accepted, then I will give you not just 100 in the project, you will get 100 in the course. So a little incentive to have some fun and see if you can find something new. And certainly I will help you find something new because I want you to get papers and you want to get papers because that's how you get grants and all of these fun things. So other logistics about this course. So we're not going to have weekly lectures of any kind. Instead, what we're going to do is the course has been divided into 4 main topic areas, which I'll discuss at the very end of today. And I'm going to do an introductory lecture to each of those 4 topics. And today is your first introduction. And so you're going to have one lecture roughly every 3 weeks or so. And I'll post the dates to Piazza once we get closer to them. And this is just going to serve as an overview of what is this current section of papers about? What are the big results we're looking for? And what are the big open problems that we have right now? And so that's what I will be doing for you. And these are going to be live streamed to Twitch, but they're also going to be uploaded to YouTube. Now, if you are unable to access Twitch or YouTube, please do let me know, and we can look at an alternate form of getting these lectures to you, but it will probably be a fair bit of a lower quality, simply because these videos actually end up being quite large. Now, from your end, what I would like you to do for your paper presentations and your project presentations is I would like you to do a pre-recorded presentation of yourself. Now, you can use your cell phone, you can use your laptop. If you have a webcam, you can do that as well. But record your presentation, and then what we will have you do is upload a link to your presentation. You can make it private and just so that only we can see it. And we'll have you upload your presentations to Piazza so that other students can then watch them. So you only have to do 3 presentations the whole term, each one between 10 and 15 minutes. I think the project ones are a little bit longer, just to mimic conferences. And then just to reiterate again, all of your participation and question grades, that's all going to come through discussion through Piazza. All right, so that's the boring stuff. What I'd like to do now is actually start talking about stereo 3D, because that's what you're here to learn. So, stereoscopic 3D is something that we see a fair bit of these days, especially if you go to the movie theater. Now, admittedly, it's not as popular today as it was about 5 to 10 years ago, but we are still seeing all of the big Hollywood blockbuster films, the superhero, the action films, the science fictions and fantasies have a tendency to be released as stereo 3D. So if we were to look at the upcoming film lineup, the New Mutants, that's supposed to be released in 3D. The new Wonder Woman is supposed to be released in 3D, and I know my daughter is looking really forward to that movie. And Black Widow is supposed to be released in 3D. All of these movies are supposed to have theatrical 3D releases. Okay. Well, what's really interesting is it probably seems like 3D is really, really new, or at least it hasn't been around that long, and that's actually simply not true at all. So some interesting things is that there's been these different eras where 3D has actually been popular. So one era where 3D was super popular was actually the 1950s, and that's actually known as the golden age of 3D. And a lot of directors at that time were actually producing 3D films. For example, even Alfred Hitchcock, Dial M for Murder, was filmed and shown in 3D. And then you've got movies like Buona Devil and all these other horror action movies. This didn't last very long for various reasons. There's another 3D era that went through in the 70s where they made some improvements to the technology, which surprisingly came mostly from the horror and porn industries. But those improvements led to a small resurgence of it. Quickly went away again because people got bored of it. But you might be thinking, okay, so it goes back to the 50s. No, it's even older than the 50s. So on the screen here, on I guess it's my left, you'll see there is this old black and white picture. This is from World War I, and it's a 3D photo. There were 3D cameras in World War I, and many of the photos that were taken during World War I were actually 3D. And so there are just archives and archives of these 3D World War I photos, which are actually pretty cool. And I had an opportunity, I guess it was about 5 years ago, there was a movie called Soldiers' Stories, a documentary. And they had collected up a bunch of these World War I 3D photos and actually created a story of just the war from them. And my contribution to this documentary was actually that these old cameras and the photographers that were using them didn't necessarily know how to take a good 3D photo. And when we take their 3D content and we tried to display it on an IMAX screen, it was so uncomfortable that we had to fix it. And fortunately, I had a method to do so. So I repaired about 5% of the images in that documentary I actually repaired. Now you might be thinking, well, 1910, that's really old. Surely 3D can't be older than that. And it is. So stereo 3D and the ability to create and view stereo 3D content goes back to 1832. It is very, very old. And what's interesting is there have actually been stereo cameras for the same amount of time that there have been regular 2D cameras. So this idea of stereo 3D is massively old and has been used for many, many different things. Now, another interesting thing is in the 1800s, you might have thought, well, stereo 3D it probably existed, but nobody used it. Actually, without TVs, stereo 3D was a very popular form of home entertainment. And I've heard that it wasn't uncommon for nearly every single household in the 1800s, at least the late 1800s, to actually have a stereo viewer. So this is very, very old technology. It's very, very cool technology. But in the over 160 years that we've had it, there are a lot of problems that we have not fixed. And maybe we can help with that. So I guess the first question, and I have to apologize, I tend to address stereo 3D from the perspective of making movies. And that's not the only way that you can address stereo 3D, but certainly the algorithms that we need to make 3D movies are the same as the algorithms we need to do things for like autonomous driving cameras and estimating depth. So how do you make a 3D movie? Well, before we can talk about how you make a 3D movie, we should probably talk about what stereo is and how it works. So there's this concept of stereopsis, and that is the fact that you have two eyes, and the eyes have a horizontal shift between them. And each of your eyes actually sees a slightly different image. And if you don't believe me, an experiment that you can do is hold your arm out at this length, and with your thumb up, close one of your eyes and put your thumb over an object in the distance. And then without moving your hand, it's very important you don't move your hand, switch eyes. And what you'll see is that the objects you were covering with your one eye is no longer covered when you switch the eyes. And that's simply because your eyes are separated by a certain distance. Since each eye sees a slightly different picture, your brain is going to interpret the distance between the picture where the object is in one and where the object is in the other, that gets interpreted as depth. That's stereopsis. So you have two eyes, so you get two images. Now this is a shot from Avatar, as I'm sure many of you have seen, and these two images look very, very similar, but if you look very, very closely, you will actually see there is a slight horizontal shift between them. And it's not a consistent shift between the two images, like each pixel hasn't just been moved over by 10. The amount of separation or shift varies according to what you're looking at. So you can see here in the bottom the amount of separation between the shoulder. We can see more shoulder in the right than in the left, but you can see that there's not as much separation in the pupil of his eye here. Now, so our brain's going to take those two images and it's going to look at the separation between each point and interpret that as depth. Now, if we're talking about terminology with respect to stereo 3D, this is where things get very confusing, unfortunately. You've got a bunch of different industries who all are using the same technology, but they haven't exactly gotten together and agreed upon any set of terms. So depending on who you're talking to, depending on what paper you're reading, you're going to see a lot of terms and you're like, what is that? How does that relate to this other thing? Only to discover it's the same thing, just another name. So some of these are, and we'll go over each of these in detail. We've got disparity, separation, and parallax. And then disparity maps and depth maps. Terms such as interaxial, interocular, and baseline. Accommodation and vergence, and this concept of epipolar geometry. So I'd like to go into each of these terms here just to explain briefly what they are, so that when you start reading the papers, you won't have to be rushing for in the nearest dictionary or Wikipedia. So to start off with, disparity, separation, and parallax, they're all the same thing. And depending on who you talk to or the context, they will use different terms. So I have here a computer-generated image, and what I want you to pay attention to is the candle wick of this candle right here. Now, if you look at the position of the candle with respect to the right edge of the image in the left plane, you'll see that it's very close to the left edge, has a distance of m. And then if you look in the right image, that candle wick is much further from the right edge, a distance of n where n is greater than m. Well, if we were to actually, and I don't have the line here, but if you were to actually draw on the left image where that n is, the difference between m and n is the disparity, the separation, or the parallax. It's how much distance from where it is in one eye to where it is in the other eye. Now, that's an interesting observation. So there's a few more terms associated with disparity. We have the concept called zero parallax. And essentially what that means is zero separation, or disparity is zero. It's saying that there is where that candle wick is in the left eye is exactly the position it is in the right eye. No separation. What we like to say that means is it appears that it's on the screen. Then we say positive parallax or positive disparity is anything that is going to be behind the screen. And then anything that has a negative separation, a negative parallax, or a negative disparity, that is things that is going to be coming out at you. So zero is flat. You're not really perceiving any depth from it. Positive is it's way in the distance. And then negative is it's coming out of the world and in your face. Most of the time, we deal with negative parallax or negative disparity. Now, most algorithms to deal with stereo 3D content need to use what's known as a disparity map, although some of them use a depth map. And we'll talk about the differences between those two in a moment. This here is actually what you see on your screen here is the disparity maps for that ray traced image you saw back here. The color of each of the pixels in this disparity map is telling me where I can find the corresponding pixel in the other view. So if I look at the front of this ball here, let's suppose that the disparity here was 55. That's the intensity of the pixel. So the disparity is 55. That means that from my position X in the left image, if I subtract 55 from X, that's where I can expect that same pixel to be in the right image. And to go from right to left, instead of subtracting the disparity, you would add it. So these disparity maps tell us the separation between two corresponding points. And for the record, this is the nicest disparity map you're ever going to see. Now, disparity map or depth map. When you're reading various 3D papers, you may see, didn't mean to wiggle my table there, you may see people refer to depth maps instead of disparity maps. I want to point out that while these two things are related, they are definitely not the same thing. They are very different. So to point out, we have depth is equal to F times B divided by D. Now, what does all of that mean? This equation here is explaining how depth and disparity are related. And they are related. You can convert disparity into a depth map and a depth map into a disparity map using this very formula here. So what are these other terms other than depth? So D is going to be the disparity. And then F is the focal length and B is the baseline, which I'll explain what that is later. But both of these parameters here, F and B, you need to know, and they are properties of your camera or whatever setup you're using to capture your 3D content. If you do not have the focal length and baseline for your disparity, for an image, you can estimate what they are, but know that it won't be very accurate. And you may have a bit of a distorted depth map as a result, which may or may not matter. Really depends. So what is baseline then? So we have interocular, interaxial, and baseline. So the interaxial or baseline is the distance between the camera lenses. So of course, if you have two eyes and each eye sees a different image, if you're trying to take a 3D photo, well then you should probably have two camera lenses, one for each eye. So the interaxial or baseline is the distance between the centers of those two lenses. Whereas the interocular is supposed to be the distance between your eyes, so from here to here. Now, I have seen people refer to the distance between the eyes as interaxial. I've also seen people refer to the distance between the camera lenses as interocular. Again, lots of confusion in the industry about what term should be used in what place. Essentially, if you have two capture devices, the inter-whatever or baseline is the distance between them. Now, how does the distance between the two cameras or your two eyes impact how much depth you are perceiving? So if the interaxial is small, that is your eyes are really, really close together, or the two cameras are really, really close together, then you're going to have less separation because the cameras are closer together, therefore there couldn't be as much separation. And therefore you have, with less separation, less depth. So if you want to make a flat image, you use exactly one lens because there would be no separation. And then as you slowly increase it, you get more and more separation and therefore more depth. So if you have a really large separation between the cameras, you get a lot of depth. And you might be thinking, why would you do that? That's not natural. Well, you can actually create some pretty cool photos with it. A friend of mine at Adobe Research has taken a stereo camera and up to the top of, I think it was the Seattle Space Needle, and he took a photo from like way on one side and then way on the other and got these really cool macro stereo photos, which is kind of neat. All right, now these terms are not confusing, but they're very important to understand what they mean, and they are accommodation and divergence. Now, you won't usually hear it referred to as accommodation and divergence. You'll usually hear it referred to as accommodation and convergence. But I've used the term divergence because it describes a more general concept. So this is properties of the human visual system. So accommodation is your ability to focus on something. So let's say you're looking in front of you at an object. Your eyes need to be able to focus on that object. That's accommodation. Vergence is your eye's ability to move slightly outward like that, yes, away from each other, or pointing inward towards each other to actually look at a particular object at some given depth. So if you were to actually film yourself looking at an object, I guess I have a pen here, really close like this experiment is not going to work. But I'll explain why in a minute. So let's see here. If you watch my eyes, even though this is a bad example, if I move this pen and I focus on this pen, you should see my eyes move inward to converge and focus on this pen. And together, accommodation and divergence are your ability to focus on an object at a particular depth. Now, if you were watching that video and I don't know how good the focus is, you probably noticed my eyes didn't actually move to focus on the pen, because the dark and dirty secret is I am completely stereo blind. I cannot see 3D or depth at all. I have been tested many times. I have never been able to see it ever. And one of the papers that you might read, if you choose, will explain why I am that way. And yes, I realize the irony that my research is something that I cannot see. I have a totally unbiased approach to it because I will never know if my results are good or bad. I rely on studies. All right, that's enough of that. So one of the interesting things about accommodation and divergence and why it's really important to mention this, and this is a mistake that Hollywood makes all the time in their movies, is they're creating artificial depth. They're faking a 3D world, tricking your eyes into thinking that there's objects there, even though they're not. And so your eyes are accommodated to focusing a certain amount for an object at a specific depth. And so if you have an object and say it's the main character on the screen and you're supposed to be focusing on their face, but the accommodation and divergence don't map for an object at that particular distance, it actually causes the viewer a great deal of discomfort. And what's interesting is it varies per person. So some people might find it perfectly comfortable, whereas the person sitting beside you may not. This is a tricky problem. All right. Now, one of the last terms that I kind of want to explain here is this epipolar geometry. This is the geometry of stereo. And essentially what it's describing is how the disparity works. How do you get that separation? So effectively, and I'm not going to explain this in any kind of great detail because it's useful for sometimes, but for other times, sometimes it's easier to understand just disparity straight up. But essentially, this OL and this OR are your optical centers, i.e. your eyeball or the camera, for the left and right planes, or left and right views. And then we have some point at a distance, x, and that's what we want to look at. So our eye on the left is going to look from the optical center through to x, and where it intersects the view plane, we get XL. And then in our right view, we are looking with optical center OR at position x, and where that line intersects the image plane, you get XR. So you get this triangle between OL, X, and OR. And then what you're seeing is EL and ER are called the epipoles. That is a line between the two optical centers, which may or may not pass through the image planes. And you can actually see that as some separation there. So this is the basis of the stereo mathematics, and it's explained a little bit in some of the papers, and so I would like to give you an opportunity to read a bit more about it there. All right. So I've kind of suggested how one might acquire then a 3D image, but let's actually talk about it. So you need two images. You need one for your left eye and you need one for your right eye. So you could use a 3D camera. And there's lots of different 3D cameras. I've actually got this one that's in this image there right here. And when you open it up, what you'll see is, like the photo, it's got two cameras. And then these actually have separate CCDs. So there's one CCD, that's the capture plate for the left, and one for the right. And then, of course, the baseline is the distance between, or the interaxials, the distance between these two lenses here. Now, this is a very old camera. This is a Fuji W3. They're no longer in production and haven't been for a very long time now. But if you've had a Nintendo 3DS, it has two cameras. There are also some cell phones out there right now that also have multiple cameras and are capable of taking stereo 3D photos. Now, these are really nice because they're kind of grab and go. You grab it, you go outside, you take a photo, and it's 3D, and you're done, sort of. The downside, of course, is that you have a fixed baseline. You can't physically move the lenses in this camera. They're screwed and glued in place. So that's one option you can do for getting a 3D image. Another option, and this is closer to what Hollywood would do, is to use two cameras. Now, this particular image, what you're seeing here is what's known as a side-by-side rig. That is, you have some metal tracks and you have two identical cameras side by side. And then you can decrease the separation by moving the two cameras together, and you can increase the separation by moving them further apart. Now, there's a few tricks to using the particular rig you see here, the side by side. You have to make sure that both cameras are actually going to take the photo at the exact same moment. A little bit of electric, and you can solve that problem easily. One of the things you can't solve easily, though, is the fact that you are restricted in how close together you can get these two cameras to be. So, and the reason for that is if you look at the size of these camera bodies, they're really, really big. So you are actually restricted in what your baseline can be by the size of the cameras themselves. What you will actually see used in industry isn't the side-by-side rig, but what's known as a beam splitter rig. And I'll post an image to Piazza here. I don't have one off right now. What a beam splitter rig is, you have one camera that points up. And yes, I know this makes no sense. And then you have one camera that points out. So you've got cameras pointing like this. And then what you have right here at a 45-degree angle is a 50-50 mirror. And the idea is 50% of the light will go to this camera and 50% of the light will go down into this camera. Now, the interesting thing about a beam splitter rig, aside from being more expensive, is because the cameras aren't actually side beside each other, you can actually get as little or as much separation as you like. Obviously, we don't want too much separation. Okay, so that's another way you could do it. But if you've only got one camera, that actually doesn't preclude you from taking a 3D photo. In fact, I've got my cell phone here, which only has one camera lens. What you would do is very, very carefully take one photo, shift your camera, and take the second photo. Now, that will let you take a still photo. I don't know about you, but I can't hold a camera still to save my life. That's why I have a tripod. It works okay for still images, but what it doesn't work very well for is if you wanted to make a 3D video, because you can't take one video and then ask everybody to do it again and expect it to match up exactly. So this works sometimes, but not most of the time. Okay, so there's some different 3D technologies that we could use to take what's known as native 3D content. Now, you might have been thinking, but that was actually pretty easy. Why the hell do we have a whole course dedicated to talking about this? There's nothing hard about that. You're right. There's nothing hard about pushing the button on this camera here. But just because you have a camera and you can push the button on it doesn't mean you took a good photo, and it really doesn't mean you took a good 3D photo. So, there are lots of problems that can come up. For example, you could have inconsistencies between the left and right view. And this may not seem like a problem, but it is. If you think about how the human visual system is getting depth from an image, we have an object in our left eye, and our brain is looking for where that object is in the right eye, and then using the separation to estimate the depth. Well, what if there's no match for that object in the other eye? What if the apple is red in one eye and green in the other? And in this particular image from Avatar, I added the specular highlight here, this little lens flare. It's only in one eye. What happens? Well, the brain doesn't know what to do because it can't find a match. And so you can get this phenomenon known as binocular rivalry happening, which can cause the viewer a lot of headaches and pain. And what some people can even see with binocular rivalry is they may see the left, right, left, right, left, right, left, right, left, right. They may be seeing the images alternate. That's really bizarre. Admittedly, I've never seen this in my life, but I'm sure you have. And I have a wonderful video that is a great example of binocular rivalry called chiral eyes, which I will post a link to it. And if you have anaglyph glasses, you'll be able to watch it and get a very bizarre effect. When I was in the theater they were demoing this short, everybody was in such pain. It's a really cool video. Everyone was in such pain though, and of course I felt nothing because I can only see one of the images at any one time, so it's a cool thing. Anyways, inconsistencies. That's a big problem. And you might be thinking, well, I'll hold the camera really still, we'll take the photo really, really quick, I won't get an inconsistency. I've been using one of these cameras for about 10 years now, close to 10 years. Might be like 8 years. And let me tell you that the first 2 weeks that I used this camera, my finger was in half the images. And you may not, that seems like a silly thing, but you're so accustomed to holding onto a camera with a singular lens that how you position your hands on this camera is so easy to get your finger in the other view. That's our fault, of course, but we may have things at the edge of the image that would be inconsistencies. It may be differences in the lighting between the two. And this is actually a problem with the beam splitter rig, is because we're using a 50-50 mirror, you get different polarization on each of the images. Now we have filters that we can use to reverse that effect, but if there are inconsistencies in the actual camera lenses, maybe one is scratched and the other one isn't, that can actually cause discomfort, and if it's really bad, it can cause binocular rivalry. So this is something that can happen with native capture pretty easily. And another big problem is too much separation. So you go out and you think, I'm going to take a photo of something. So if I were to take this 3D camera and I want to take a photo of my webcam here, we'll get right up close. And if I take this picture, my camera's actually dead, but if I were to take that picture, the separation would be enormous because the object I'm taking a photo of is right in front of the camera. And so I've got actually that much separation in the image. And that's way beyond what the human visual system can handle. What ends up happening is if you have too much separation, the human eye can't actually converge or diverge to actually look at it, and it causes extreme discomfort. So if you have too much separation, that's going to be a problem too. Now, you might be thinking, well, why don't I just plan? And indeed, this is what happens in industry. They have pretty decent technology that they can use to estimate how much separation do we need, at what distance do each of these objects need to be, such that when we display it on the big screen, it doesn't cause too many people discomfort. Now they have it, that doesn't mean they always keep to it in practice. And so it's very, very common to, when you're viewing your dailies the next day, to realize that the footage you captured the day before has too much or too little separation, so too much or too little depth. So that's another problem with native capture. So So, as I said, really easy to actually take the photo, but it's really hard to do a good job of taking the photo. Most of the stereo photos that I took with this are really, really bad. They're a lot better now, but they're still not the greatest. So now we have to ask ourselves, we've taken a 3D photo, how are we actually going to make it good after the fact? So how do we alter the separation to reduce it so it's more comfortable? How do we increase the separation to make it, give it a little bit more depth? How do you handle things like inconsistencies between the left and the right view? Do you go into Photoshop and remove them? Well, how do you make sure that Photoshop doesn't wreck things? How do you handle mirrors and reflections? That's actually a pretty big problem. How do you handle shadows and transparent regions and specular highlights? Things which naturally may actually only appear in one of your eyes. Now, I can tell you things like specular highlights in Hollywood, how they actually handle that, because it is perfectly natural for it to appear in only one eye, because your eyes are located in two separate positions. One of them may see the nice highlight and the other one may not. But what they do in Hollywood is they'll actually remove it or put it in both, even though that's unnatural. But that then starts asking questions. Does that create something that's unnatural and going to cause the viewer discomfort or confusion? We don't know. Lots of open areas in this particular part of computer graphics. Okay, so we've talked about how to do native 3D capture, that is capture with actual physical cameras. And we've talked about some of the difficulties that you can have with capturing natively. How do you fix it? Well, one of the ways that you can fix it is also one of the ways that you can capture 3D, the other way to capture 3D. And that's known as stereo conversion. Now, stereo conversion does not use a 3D camera. Stereo conversion does not use two cameras. Stereo conversion is using a single camera. And then we are going to artificially create the second view using the single view that we have. Now, this is where I wanted to actually give you a live demo of an industry stereo converter. Then I remembered I'm under an NDA and not actually allowed to show it in any public space. So pay attention on Piazza, because I may find a way to privately share such a thing with you. I'm allowed to share privately, just not publicly. But let's talk about what stereo conversion actually means. So here we have, this is an image, I believe, from Godzilla, one of the more recent Godzillas. And this was the original film footage. And then what they're going to do is they're going to consider this, and this is actually an unusual but much better method for doing stereo conversion. They'll consider this the center. And then they're going to produce an artificial left view and an artificial right view, and now they have a stereo image. So how do they produce the artificial views? This is where you have hundreds of artists in a room tracing hair. So the first thing that we need to do is what's known as rotoscoping. So we're actually going to have a bunch of artists in a room, and they're going to trace everything by hand. So they're going to trace all of the major objects. So this one you can see any kind of major object in depth they've traced around. So these pillars, and they've noticed, hit the scroll wheel, that the bottom of the pillar has slightly bigger depth, so they've separated that from the top of the pillar. And then if you look at this little girl's coat, they've got her, the lapels of the coat, they've got her face, they've got the plane of her nose, her chin, her ears, and then they've done some of her hair, but not all of her hair. And then there's another little boy over here to the right, and they've got all the fur on his collar, all drawn by hand. So that's step one, rotoscope. And they have to do this to every single frame of the entire movie. You're looking at hundreds of thousands of images they have to trace. Now, the particular stereo conversion tool that I have worked with would then have another group of artists create very rough 3D models of all of the objects in the scene. And that's what you're actually seeing here. We've got a rough 3D model of this girl's face. And you notice it's really balloonish. We're going to fix that. So we've got kind of a balloonish model of the background world, balloonish model of the hair. So we've got a rough 3D model. And then what they do is they take the roto lines and they're going to combine them with this mesh, and they use the roto work to cut these balloonish meshes. And then to get the two views, they project the film back onto the 3D model, and then they have two fake cameras in this fake 3D world, a new left camera and a new right camera, and now they have a left view, and now they have a right view. Now, of course, one of the problems here is that because the cameras are now in different positions, they may see behind an object that the original camera couldn't see behind. And so they also have to do some in-painting to fill in those regions, which is, again, another open problem. And how it tends to be filled right now is using interpolation and then having an artist manually correct anything that doesn't look so good. Could we do better? You bet we could. So in order to do stereo conversion, and this, by the way, is conversion from a Terminator, you have a lot of manual labor going on. Now, this rotoscoping. This is actually an interesting problem, and something that there's a reason why you might be wondering, well, why don't we just use a segmentation algorithm? Because wouldn't that give us the edges of each of the objects that we want? And that's a nice idea, but there is a reason why we actually use humans in practice. So whether you look at edge detection or clustering or Fred fill or region growing, marching or Markov random fields to do some kind of segmentation to get your roto lines, we run into problems, such as out of focus regions. If you look at any film footage, a lot of the scene is actually out of focus, and even the object that's supposed to be in focus is surprisingly out of focus when you actually look up close. So how would you use these algorithms to do edge detection for out of focus regions? And by the way, how it was handled for us was they did an outer edge and an inner edge. And then in between them, they knew there was some amount of blending. And that's another complication. How do you handle the blending? Then you have to look at, well, what about a whole surface versus a pattern segmentation? So if you have a wallpaper with a floral pattern on it, a lot of these segmentation algorithms would actually give you the lines around each of the flowers on the wallpaper. But those flowers have no meaning in depth because they're just on a flat wall. So you don't want the flowers drawn. You just want the wall. So how do you tell a computer model to differentiate between the pattern and the actual depth of the object? You can actually kind of see it here in this kitten picture. This kitten is sitting on the edge of a wall where there is a mirror. So a computer might actually segment and give you lines for the reflection of the cat. But a human would be like, well, that's a reflection. So we're going to handle that differently. So you've got patterns that cause problems, out of focus regions that cause problems for rotoscoping. You've got problems arising from reflections. You've got problems arising from transparencies and semi-transparent regions. This ends up getting done by a human or minimally aided by a computer, usually mostly done by a human. Then, of course, the mesh generation. That in itself is a big problem. Are you going to have a human create those meshes, or are you going to have a computer try to guess what they are? How concave or convex are you going to make them? How round do you make them? How do you handle mirrors? How deep? How do you handle the transparencies? There are lots of issues here to solve. So, native capture or conversion. Native capture at this point is probably looking pretty good to you because the problems probably seem a lot simpler and a lot less manual labor. And you're not wrong, but some of those problems are really, really tough and we haven't solved yet. What's interesting is despite the manual nature of stereo conversion, over 95% of films that you've seen in the last 10 years were converted. All of those Marvel movies, Black Panther, all of that, they're converted. Avengers, converted. Even the films that we did capture natively, so things like Planet of the Apes and Days of Futures Past, they were captured natively using stereo cameras. Movies like Pompeii, that was captured natively. They still have segments of the film that were converted. And the reason is we don't know how to solve many of these problems of separation. We don't know how to solve a lot of these problems with inconsistencies. We don't have some method to correct that works well. And so Hollywood's solution is one of, well, we could convert it. And so as a result, what you can tend to see is movies that were filmed natively end up having a lot of sequences converted where they found some mistakes in the stereo. And instead of going and recapturing, they've just said, you know what? We'll just convert that part. Is that the only way that they handle it? No. Unfortunately, this is a common thing that happens as well. If I ignore it, maybe it'll go away. Maybe my audience won't notice that there's a big problem with the 3D here. This happens, unfortunately, but you tend to notice when you're actually watching a 3D movie, you'll see people take their glasses off because there's something so bad that people can't even stand to look at it. The problem of ignoring is that you're going to be causing your audience serious discomfort. If you cause them discomfort, they walk out of that theater and they're going to tell all their friends how bad it was in 3D. And so they won't actually go and watch the movie in 3D. And that's bad because Hollywood is counting on you spending that extra few fistful of dollars to watch the 3D version instead of the 2D version. So you don't want to do this option. So you could do conversion. You could bring everybody back and do a reshoot. So you mixed up the stereo. Let's bring everybody back in. We'll do it again. Okay, well, what if you had to set your set on fire? So in the movie Pompeii, they had to film it in an order such that the pre-volcanic explosion got filmed before the post-volcanic explosion because they actually had a lot of fire. So you can't, if you've already done the fire scenes, you can't go back and refilm because the sets don't exist anymore. They're on fire. They were burned. Or maybe simply you can't, maybe your actors have gone and they're working on another movie now. Or maybe you were filming a sports event. You can't call the Penguins and the Capitals back in to have another hockey game and do it exactly the way they did before. So it's not, ignoring it is a bad idea. And you might think that bringing everybody back in to reshoot is a better idea, but it's not always possible. And it's very, very costly to do. So, of course, that's where doing conversion or redoing the conversion actually comes into play. This, by the way, is from Thor 2? Yes, Thor 2. I just watched it the other day, so I should know. And I feel like these days, conversion works reasonably well, or so I'm told. And it just ends up people would rather just do the conversion of it. It's getting cheaper. It's getting better. Let's just convert it. All right. So this has been all about how do you actually make the 3D content. And hopefully what you're taking away from this is there's lots of different ways that you can actually create 3D content. And you can even do it at your home. And I would try it. If you have a cell phone or a camera, try to take a 3D photo. And I'll post a link on Piazza for how to view said 3D photo on your home laptop if you don't have a 3D screen. But one of the things I want you to get away from this as well is that creating 3D content, even though it seems like it's fairly straightforward to do, there are many costly, uncomfortable errors that can arise from it, whether you're doing native capture or a conversion. And that in order to repair those errors, it's either going to be at the expense of your audience or it's going to have significant manual labor involved. And so this is where, as computer scientists, we ask, can we help this process? And hopefully over the course of this term, you're going to see some ways where you can help. So that's about making 3D content. How do you view 3D content? So, first up, nothing special is required in order for you to do this. This is known as free view. This photo, by the way, is known as the creepy baby. What you do is, well, what I'm told you do is you sit in front of it and you try to make sure that your left eye only sees the left image and your right eye only sees the right image. So you may have to sit at a certain distance away from this in order to actually get the 3D effect. So this is one way, just stare at the side by sides. And I've seen some people be quite successful at this. I think it's probably kind of awkward. A variant of it that people tend to be a bit more successful with without using any special equipment is known as the cross-eyed view. So you're going to switch the places of the left and right image, and then you cross your eyes, and then you should be able to get the depth as well. And again, I will post some 3D content, and you'll have an opportunity to actually try to do this. Now, if you don't want to do this rather experiment here, another way that you can actually view stereo content is using a stereo viewer. And again, since we don't have an in-person class, you aren't going to get to play with some of this tech. But maybe you have one at home. So if you look at this one here, I think this is an early 1900s stereo viewer. And you can see here that they have a stereo card, and it's got the left and right. And then this special viewer here with a separator that makes sure that the left image goes to the left eye and the right image goes to the right eye. And this kind of viewer here is what people used throughout the early 1900s. And there are various names. I think this one, the name escapes me at the mind. It's not the Wheatstone viewer, it's the other one. I'll post the name later. Now, a more modern version of this, and maybe you've used one, is good old-fashioned ViewMaster, which in itself is quite an old tool. And I should have brought one up from my basement. What it is instead of being able to view a singular stereo image, you have these cool wheels, and the images on the opposite side of the wheel are the left and right. And then you get 7, I think it is, views per wheel, and you click a button, and it works just like the stereo viewer, making sure that the left goes to the left and the right goes to the right. But now instead of a single image, with a push of a button, you get to watch 7 images. And I had these as a kid. I never understood what was so cool about them, because you hold them up to the light and you get to, click through watching Cinderella or something on them. But I didn't get it. What was the point? I could just watch the movie or read the book and it was no different. Of course, because when I was a kid, I didn't realize that I was stereo blind. Now, another technology that you can use to view stereo, and is very, very common and also very, very old, is using anaglyph glasses. So the whole idea here is you're going to apply a color filter to the left and a separate color filter to the right. And typically, it's going to be red and blue. And if you do red and blue, you can watch grayscale images. And if you want to have some color, and it's not perfect color, you use red and cyan. And so then you wear a special pair of glasses that have the appropriate filters on the appropriate eye, and you look at the image here. As you can see, these are both anaglyph images, and it will separate and give the left image to the left eye and the right image to the right eye. Now, by the way, this is another one of those World War I photos. So this technology is really easy to create, and I'll put instructions for how to create an anaglyph on Piazza as well. And that way, if you have anaglyph glasses, or you can acquire some anaglyph glasses, you'll have a way to actually view some of this content. It seems really easy, but one of the problems that you get with anaglyph is this concept called crosstalk. Now, what crosstalk is in order for this to work out, the filters have to be applied to the image, have to match the anaglyph glasses exactly. Because what can happen if there's slight variations in the filters, how they're applied to the image and the glasses you're wearing, is some of the red image will leak into the blue eye, and some of the blue image will leak into the red eye. And so you get ghosts of the other view in your view, and that can cause some minor discomfort or some confusion as well. So anaglyph works, but it's really, really prone to crosstalk, especially if you're dealing with computer screens and really, really crappy anaglyph glasses, which, let's be honest, all the anaglyph glasses I have are really crappy. Now, you might be thinking, is this how they watched 3D movies in the 1950s? Because you may have seen a National Geographic photo where people were in a theater and they're all wearing anaglyph glasses. And I'm going to tell you a secret, that image is a lie. Because this is how they did 3D in movie theaters in the 50s. The exact same way we do it today, which is using another kind of anaglyph, but instead of it being red and blue filters, we are now using polarization for our filters. So what you do is each of the lenses is capable of filtering against a different kind of polarization. So one of them is like a circular polar and the other one's not. These are the same glasses that you would use today. Now, there's different ways that you can actually project this content. It's typically projected on a silver screen, not a white screen for brightness. How it tends to be done in theaters today, or if you have a 3D TV with, these are called passive stereo, by the way, because the glasses don't do anything. And how it tends to be done today is you'll have your TV or your projector will rapidly switch between showing you the left and the right view at a rate of something like 240 frames per second, which is beyond what you can really perceive. And the idea is that the impressions on your left eye and the impressions on your right eye are coming at a rate fast enough that you think you're getting both images at the same time. And this is actually how RealD in the movie theater works, is they're alternately projecting left and right to you at a rate that you can't perceive, but you think you're getting both at the same time. So that's kind of cool technology. Now, unfortunately, while this technology does do better than the red-blue anaglyph in terms of crosstalk, it is far from perfect. And you may have actually noticed this at a movie theater. And what's interesting is the next time you go to a theater, which who knows how long that's going to be, go to a 3D movie and turn your head just a little bit, just a little bit. That polarization is directionally sensitive. And if you turn your head just a teeny tiny bit, what's really cool is you get really strong crosstalk and you'll end up seeing both images in the same eye. That's tricks I play at a movie theater. Everybody looks at me weird, but there you go. That's what the 3D researcher looks like when you go to a 3D movie. So these are subject to crosstalk. Another downside of using these polarized glasses is that the image becomes darker, so it's not as bright and as vibrant. Now, this is partly the glasses' fault, and it's also partly the projector's fault. If the projector's bulb is not is old and it's not projecting at the same brightness, then an image is going to appear very dim. So passive stereo, these glasses that do nothing, they're very easy to use. They're very cheap. But unfortunately, they're really subject to crosstalk, and they're not as bright or not as colorful. Now, if you're using stereo at home, or if you're at a super fancy 3D movie theater, you might get to use what's known as active shutter stereo glasses. Now, these glasses look very similar to polarized glasses, but they are very different. These glasses are not cheap pieces of plastic that you want to throw out. These lenses are actually LCD screens, and these glasses have power. And what these glasses do is, at a very rapid rate, black out alternately left and right eye. So you can't perceive that your left eye is seeing black because it's happening at such a rate of going back and forth, black, 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 that you just think you're looking straight through them. Now, the glasses on their own aren't enough. They have to be in sync with the screen or the TV. And the TV is going to project, just like with RealD, the left and right images alternately at a rate that matches the glasses blacking out the opposite view. And this happens so quickly that the human perceives that they're seeing both images at the same time, even though they're not. Now, you do get better color, not perfect. You do get better brightness, not perfect again. It didn't eliminate crosstalk, unfortunately. It's better, but it's definitely not perfect. And so it is a better viewing experience. Maybe when we're back on campus, I can let you check it out because we have one of these screens. It's not perfect, but it is better. Unfortunately, these glasses are really, really expensive and very, very fragile. All right. Are there any other options for viewing stereo 3D content? You bet there are. Many of you have seen these. There's something called lenticular prints. When I was a kid in the 80s, you used to get lenticular prints in your cereal boxes, and they were cool. You kind of turn them and you see two different images. Again, I didn't realize I should be seeing a 3D image because I didn't know. And if you actually touch a lenticular print, it's very bumpy, and it's bumpy because there's a special lens, and that's what this background here is, over top of the image. And the idea is one eye is going to see going into the lens this direction, and the other eye will see going through the lenses on this direction. And so to make sure each eye gets the correct image, we actually alternate thin slices of the left and right, so that when they look through the lens, each eye looks through the lens, they get projected the correct value. And if you turn your head like this, you can see a whole bunch of different ones. And what's cool about lenticular is it's not limited to just like doing a stereo 3D. It's not limited to left and right. I think you can do up to 11 different views. So you can actually get like a whole really rounded effect. And if you want to do stereo, something that I don't have here, there's also something similar called a wigglegram. And that's just on your computer screen, make a GIF where you alternate back and forth pretty quickly. So lenticular is really common. And in fact, you can even get, these are called auto stereoscopic screens, by the way, because you don't have to do anything to get the stereo effect. You just look at it. The screen on the back of this camera is actually a lenticular screen. Then we have a similar screen called the parallax barrier, which again, you're alternating thin strips of the left and right images, but instead of a bumpy lens on the top, you have a barrier where the eye can only see at a particular angle behind it. And this is actually what the Nintendo 3DS uses. When I just look straight at lenticular versus parallax barrier screens, look, if I compare the screen on this camera to a 3DS screen, I personally think the parallax barrier screen is a little bit more clear, but that just might be because this camera has a cheap lenticular screen. I'm not sure. Maybe you have some of these screens and you can tell me your experience about it. Now, there are other things called light fields or light field TVs, and that's actually what I have in our lab, which is actually a kind of lenticular screen. It's just that it's a much better technology. You don't really see the bumps in the lens in the front of the TV. So we actually have in the lab, if we ever get on campus here, a 65-inch giant auto stereoscopic screen. And you can view it from anywhere in the view room, because instead of just having one image from the left and right, if you're over here, the TV is also projecting other things. And if you're over here, the TV will project another stereo view as well. So it's a pretty cool screen. All right. So that's kind of a brief overview of what stereopsis is, some of the terms you're going to see a lot of, also an overview of how to capture and how to actually view the stereo content. So I'd like to talk about now just very briefly the organization of the topics. So there are 4 areas. The first area is stereopsis and stereo viewing technology. So this is going to go into much greater depth about how the human brain perceives depth, what kinds of things cause discomfort, why does it cause discomfort, what are some of the general rules that we need to obey to create good 3D content, and going into, of course, greater depth about how do some of these different stereo viewing technologies actually work. So that's the first module. The second one is about conversion and disparity maps. That's probably one of the biggest areas because conversion is very much an unsolved problem, as is producing disparity maps. And you can't really do much with stereo without a disparity map. So it's a very important topic. The third area is stereo manipulation. So here we're looking at things like, oops, there's a bird in front of in my picture and I don't want that bird. How do I remove it? Or how do I edit the stereo image? How do I edit a stereo video? How do I apply any kind of stylization? Maybe I want to create a painted stereo photo. How do I do that? So how do we actually take stereo content and a disparity map and manipulate that image? And then the final section is talking about perception and applications of stereo 3D. So things like How does viewing stereo content affect people's motor systems? How does it impact engagement with a game? And applications, what other things can we use stereo 3D for other than watching movies? And what kind of impact does that have on our viewers? So again, these last slides just go into greater detail about those different things. So then what you will see on Piazza, and again, if you don't have access, please send me an email right away. You will find a list of all of the papers that we're going to read this term, and it may grow a little bit depending on how many new people join the class. So if you haven't registered and you'd like to register, let me know. I'm more than happy to expand the class size for more people. It will require I add more papers. So there's a sign-up sheet. It's a Google spreadsheet. It's first come, first served. You can argue amongst yourselves as to who gets to present which paper. I'd like you to choose 2 papers, one from each one from a different group. And then I'd like you to choose 8 papers to read and review, 2 from each of the groups, and then 24 presentations to actually review. Divide that by 4 for each of the different groups there. So the sign-up sheet and list of papers are available on Piazza. You can download the zip file containing all of the papers off the course website. The paper review and presentation review forms are also available on Piazza as well. So we are out of time for today. We can talk more on Piazza, but I hope you are staying safe and happy, and I hope this is going to be a really fun course and you all learn really great things about 3D.